Finally, we talk about enzyme inhibition. There are two general types of enzyme inhibition. We have the reversible and the irreversible. First, we will talk about reversible inhibition. We have three types of reversible inhibition. The first one is called competitive inhibition. We have another molecule called the inhibitor. From the name itself, it inhibits the reaction, which is basically the enzyme catalyzing the transformation of your substrate to the product. In competitive inhibition, your inhibitor binds on the active site. So it's competing with the substrate. This affects the affinity of the substrate because you have your inhibitor present there. That is why there is a factor here, alpha factor, multiplied to the Michaelis-Menten constant. So this is to account for the apparent affinity of the substrate to the enzyme in the presence of the inhibitor. Now, your maximum initial velocity is not affected. So, in your Lineweaver-Burke equation, if you compare your plot without inhibitor and your plot with inhibitor, you will see that you will still have the same y-intercept, but the slope is different. So the consequence of that is you have a different Km in the presence of the inhibitor. So just like what we see here. So the y-intercept is retained, but since the slope changed, you have a different Michaelis-Menten constant in the presence of a competitive inhibitor. The second type is called uncompetitive inhibition. The inhibitor binds to the enzyme substrate complex. Now, since the substrate is already bound to the active site, your inhibitor is binding on a different region of your enzyme. So the effect now is on the rate of the chemical reaction. That is why we have alpha prime here together with the maximum initial velocity. If you compare the Lineweaver-Burke equation without inhibitor and with inhibitor, you will see that the slopes are the same, but you have a different y-intercept. So the consequence is you get a new value of Vmax and a new value for the Michaelis-Menten constant. Finally, we have the mixed inhibition. Here, your inhibitor can bind to either the free enzyme or the enzyme substrate complex. That is why it's called mixed inhibition. Again, your inhibitor binds on a different region of your enzyme and not on the substrate. But this binding affects both your Michaelis-Menten constant and your Vmax. That is why you have the alpha factor here and the alpha prime. If you compare your Lineweaver-Burke equation without inhibitor and with inhibitor, you will see that all of the parameters are different. You have a different slope, a different Vmax, and a different Michaelis-Menten constant value. So take note the trend for each of these type of inhibition. So here's a summary. If you have competitive inhibition, you will get a different Km value, but the same Vmax value. The slope will also be different. For uncompetitive inhibition, you will have different value for Vmax and for Km, but the slope doesn't change. And finally, for mixed inhibition, you will have different values for Vmax, different values for Km, and different slopes. And finally, we have the irreversible inhibition, which is, from the name itself, it's something that we cannot reverse, meaning once your inhibitor binds to the enzyme, then it stays there permanently. So this is achieved often through covalent bonding. So your inhibitor creates a covalent bond to some amino acid residue in your active site. And we often refer to them as suicide inactivators. So these are actually very effective drugs if we want to inactivate some enzyme that is related to some disease. We also have what we call transition state analogs, which are molecules that mimic the transition state. So if you remember the transition state, it's an imaginary state of the enzyme, the active site of the enzyme and the substrate. So it's described by partially broken and partially formed bonds. You can actually synthesize some molecules that mimic this transition state, and this transition state analogs will have very high affinity to the active site of an enzyme. And if it has some functional groups that can form a covalent bond with a specific amino acid residue, then you can also achieve irreversible inhibition.